Hi guys, greetings of the day. Myself Raghavendra. So today we are going with design of spur and helical gear, sixth part. In the previous part, we went through design of wear, endurance strength, selection of material, and design considerations. So in this part, we'll start with design procedure for spur gear. So what are the basic steps are there to design a spur gear problems? So usually in the problem statement, they will give you the power, speed. Along with that one, sometimes they'll give you I, that is velocity ratio. So with the help of that one, unknown speed also we can find out. So like that we can do. So we'll go through step by step. In the first step, we have to identify the weaker member. So out of pinion and gear, whichever is the weaker member, we have to identify. To identify that one, we have to draw a tabular column. First column is particulars. Second one sigma naught. Third one y. Fourth one sigma naught into y. And fifth one remarks. This is the first row. Along with this one, we have to draw another two rows. One for the pinion and another one for the gear. So this row it is for pinion and this row it is for gear. So for pinion it is sigma naught 1, gear it is sigma naught 2. So it is y1 and this is y2. Similarly, this one is sigma naught 1 y1, sigma naught 2 y2. So multiplication of these two columns is fourth one. So in the problem statement, if they have given the stresses, allowable static stresses for pinion and gear, use that as sigma naught 1 and sigma naught 2 respectively. If they have not given, assume the material for pinion and gear from table 23.18. I am referring Design Data Handbook Volume 2 by Lingayya. So in that one, assume the material from table 23.18 and take the sigma naught 1 and sigma naught 2 for pinion and gear respectively. So that one we have to substitute here. So y is nothing but Levy's form factor. So that depends upon system of gear. So in the problem statement, they will give you system of gear. If it is 14.5 degree system of gear, the y equation is y is equals to 0.124 minus 0.684 divided by z. This is for 14.5 degree involute. So this equation we have in the data handbook, that is 23.115. Similarly, if system of gear is 20 degree full depth, then y equation is y is equals to 0.154 minus 0.912 divided by z. So this is for 20 degree full depth involute, and this equation is 23.116. Similarly, if it is a 20 degree stub, then the equation is y is equals to 0.17 minus 0.95 divided by Z. So this equation it is for 20 degree stub, and equation number is 23.117. So depending upon which system of gear they have given, we have to use that Y equation and we have to find out Y1 and Y2. So here Z is nothing but number of teeth. If we substitute Z1, that is number of teeth in pinion, then we will get Y1. If we substitute Z2, that is number of teeth in gear, we will get Y2. So if they have given Z1, then use that one, and with the help of velocity ratio equation, we can find out the Z2. If they have not given Z1, so we have to take Z1 from table 23.6. By referring table 23.6, there we will get minimum number of teeth on pinion to avoid interference. There also we will get that minimum number of teeth on pinion to avoid interference for different types of systems of gear. That is for 14.5 degree separate, 20 degree full depth it is separate, 20 degree stub it is separate. So by referring that one, we have to consider Z1 minimum number of teeth. We have to consider and we have to get the value of Z2. And after that one, we have to get Y1 and Y2. So by multiplying second and third column, we will get the fourth column. So out of these two, that is out of sigma naught 1 Y1 and sigma naught 2 Y2, whichever value is the smaller, that one will be the weaker. And design should be based upon weaker member. Say if sigma naught 1 Y1 is lesser than sigma naught 2 Y2 means pinion is weaker. So at that time, design should be based upon pinion. If sigma naught 2 Y2 is less than sigma naught 1 Y1, at that time gear is weaker. So at that time, design should be based upon gear. So always design should be based upon weaker member. So this is the first step. Second one, design. So in this one, we have three sub-steps. First one, A, tangential tooth load. So for this one, equation is Ft is equals to 9550 into capital B C suffix S divided by N into R. This one we have in the data handbook, that is 23.87 D. So in this one, P is nothing but the power. In the problem statement, they will give you CS is nothing but service factor. We will get this service factor from table 23.13. Then small n is the speed of weaker member we have to consider. If the weaker member is pinion means, so we have to consider N1. If the weaker member is gear means, we have to consider N2. Then R is nothing but radius of weaker member. So R is equals to diameter by 2, D by 2, which is equals to M into Z divided by 2. So M is the module and Z will be the number of teeth of on weaker member. So we will be assuming, or we will be getting this one in the previous step. By substituting that one, we will get Ft in terms of M. And we'll call this as equation number 1 afterwards. This is substep A. Next, substep B. Tangential tooth load from Levy's equation. So we have the Levy's equation for tangential tooth load, that is Ft is equals to sigma naught B Y P CV. Equation number 23.93. So in this one, sigma naught will be the allowable static stress of the weaker member. If the weaker member is pinion, we have to substitute sigma naught 1. If the weaker member is gear, we have to substitute sigma naught 2. So B is the face width, that can be taken as B is equals to 3 pi m to 4 pi m, or 9.5 m to 12.5 m. So equation number 23.132. Either by considering this one or by considering this one, we have to assume a B value. We have to select a B value. Next, Y is nothing but the Levy's form factor of the weaker member. P is the circular pitch, which is equals to pi into m. By substituting all these things in this one, we will get once again Ft in terms of m and Cv. In terms of m and Cv, and we have to call this as equation number 2. And we have to equate equation 1 and 2. And after equating equations 1 and 2, once again we will get equation in terms of m cube Cv, because this one will be in terms of m square Cv we will get. So why? Because here also mv is there, here also mv is there. By multiplying m square Cv we will get, and equating 1 with respect to 2, we will get everything. It is in terms of m cube Cv. M cube Cv is equal to some value we will get by equating equation 1 and 2. And we have to call this as equation number 3. Now, this Cv will get based upon the mean pitch velocity. Cv is the velocity factor. Cv will get based upon the mean pitch velocity. That is, Vm is equals to pi into dn divided by 60,000. So here d is the diameter. So that can be written as pi into mz into n divided by 60,000. So m will be the module. Whatever we have to keep as it is. Z is the number of teeth on weaker member. So whatever we took in the previous step, that is in the first step. N is the speed of the weaker member. So by substituting all these things, we will get Vm in terms of m once again. And it will be in terms of meter per second, because already we have divided by 1000. So we will get it is in terms of meter per second. Now by referring table 23.3, we have to assume standard m from that table, standard module from that table, and we have to substitute v in this equation to get Vm. Based upon Vm, we have to calculate Cv. If Vm is less than 7.5 meter per second, we have the equation for Cv as Cv is equals to 3 divided by 3 plus Vm. That is equation number 23.134a. Similarly, if Vm is more than 7.5, less than 12.5 meter per second, at that time we have the Cv equation as Cv is equals to 4.5 divided by 4.5 plus Vm. So that is equation number 23.135a. So like that, if it is up to 20 meter per second, we have the equation in equation number 23.136a, and if it is more than 20 meter per second, we have the equation in equation number 123.137a. So based upon this Vm, we have to use the equation of for CV and we have to calculate, and we have to substitute M and CV in this equation, and we have to check with respect to RHS. So until we get LHS should be greater than or equal to RHS. Until this one, we have to do the trial and error method. So when LHS becomes greater than or equal to RHS, so that is nothing but that is suitable. Means that module, whatever assumed, VM, whatever calculated for that module, CV, all those things are suitable. Till that one, we have to do the trial and error method. So after this one, we have to check is it correct or not. Whatever we assume the values, is it correct or not. For that one, we have to check for the stresses. That is the third step. C in the main second step. So C is check for the stress. So here we have to calculate allowable and induced stresses. So sigma allowable, which is equals to sigma naught into CV allowable. Here sigma naught will be the allowable static stress of the weaker member we have to substitute, and CV is the velocity factor when LHS becomes more than RHS. At that time, whatever CV we will calculate, that value we have to substitute and we have to calculate the sigma allowable value. Similarly, sigma induced we have to calculate, that is sigma induced is equals to, that is sigma naught into CV induced, which is equals to Ft divided by B into Y into P. We have to use this equation to find out sigma induced. So in this one, Ft is nothing but, so in A, that is substep A, whatever we will get the Ft value in terms of M by substituting that value of M when LHS becomes more than or equal to RHS, that value of M, we have to get the value of F theta and we have to substitute that one. B is nothing but the phase width. We have assumed at the step of small a, that one. Y is the Levis form factor for the weaker member, that one we have to substitute. P is nothing but pi into M. So M is nothing but when we get LHS is greater than or equal to RHS, that M. By substituting all these things, we have to get the sigma induced value. So here we have to get sigma induced should be less than sigma allowable. If we get this one, then we can say the design is satisfactory. If it reverses otherwise, then we have to change the value of M. We have to increase the M, and once again we have to go through previous steps until sigma induced becomes less than sigma allowable. So if this satisfies, so whatever you are using the M at this point, those are the final values of module and phase width. So this is the second main step, that is design. So moving to the third main step, dimensions. So this dimensions we will get from table 23.1, like addendum, dedendum, tooth thickness, total depth, clearance, outside diameters of pinion and gear. So everything we will get from table 23.1 for the given system of gear we have to calculate. And moving to the last step, that is fourth one. Checking. So in this one also we have three sub-steps. The first one is check for dynamic load. So we have the equation for dynamic load, that is FD is equals to FT plus 21 Vm into FT plus B into C divided by 21 Vm plus square root of Ft plus B into C. So this is equation number 23.155. So here this Ft is nothing but tangential tooth load. So at second main step, C part, whatever we have used the Ft, that one we have to substitute here. Vm is nothing but mean pitch velocity. So when LHS becomes more than or equal to RHS, at that time whatever Vm calculated, that value you have to substitute. B is the face width. So we have assumed at the earlier, and that one after finalizing the model, so we have to calculate face width. And C is the coefficient. So this coefficient depends upon the error F. That error F we can find out by two methods. So first one, based upon class of gear. So if we know the class of gear, then from figure 23.35a, for the given class of gear and module, calculated module, we will get the error F. If we don't know the class of gear, we can get this error F in the second method, that is with the help of velocity V or Vm. So if we don't know class of gear, then we can go with velocity V or Vm. So from this one, that is using from figure, this one is 23.34a. So for class of gear, figure 23.34a we have to use. For velocity, from figure 23.35a. With the help of this one, using calculated V velocity or Vm, whatever we are substituting here, by using that one, we can get the error F. So by using any one method, we have to get the error F. Once we get the error F, now by using table 23.32, for the selected error F, we will get the value of C. By substituting all these values in this equation, we will get FD, that is dynamic load. Second one, in this step, that is B, endurance strength. Of the gear tooth. We have the equation for endurance strength of the gear tooth, that is FF is equals to sigma SF into B into capital Y into M. Equation number 23.158. So here B is the phase width, the calculated value we have to substitute. Capital Y is nothing but pi into small y. Here small y is the Lewis form factor of the weaker member. M is the module and sigma SF is called as endurance limit. We will get this sigma SF from table 23.33. By substituting all these things, we will get FF. Always this FF should be greater than FD. And the last step, C, that is check for wear load. So we have the equation for wear load according to Buckingham's, that is FW is equals to D1 B Q into K. So equation number 23.160. So here D1 is nothing but the diameter of the pinion that can be calculated with the help of equation M into Z1. B is the face width. Q is called as the ratio factor. It can be calculated with the help of equation Q is equals to 2Z2 divided by Z1 plus Z2. Equation number 23.163. So Z1 and Z2 are the number of teeth on pinion and gear respectively. Then K is called as the load stress factor, which is equals to 1.43 into sigma FAC square into sin alpha divided by E naught. So this equation number is 23.161. So here alpha is nothing but the system of gear, that is either 14.5 degree or 20 degree full depth or 20 degree stub. So for 20 degree full depth or 20 degree stub, it is alpha is equals to 20 degree only. Whereas if it is 14.5 degree, we have to substitute it as 14.5 degree. Here E naught is called as equivalent Young's modulus. It can be calculated with the help of equation E naught is equals to 2E1 E2 divided by E1 plus E2. So this equation number 23.162. So here E1 and E2 are the Young's modulus of pinion and gear respectively, whereas sigma FAC is called as limiting stress for surface fatigue, which can be calculated with the help of equation 2.75 HB minus 69. Equation number 23.168. Here HP is the Brenner hardness number. So by substituting all these value in this equation, we will get the value of FW, and always FW should be greater than FD. Then only design is satisfactory. If FW is less than FD, so either of one or more changes we have to do. That is, we can calculate FD by decreasing error small f or decrease the module M. If we decrease the module M means we have to start from second main step only. Then either we can increase the face width B. So to increase face width B means we are assuming that is either from 3 pi m to 4 pi m or 9.5 m to 12.5 m. So we are assuming say 10 m. If we assume means instead of 10 m we have to change it to 11 or 12 m like that. But if we change also, we have to start from beginning, or the last one is increasing the surface hardness, that is HV. So by like this, we have to make sure that FW should be greater than FD. So this completes the design procedure for spur gear. Thank you. Please subscribe my channel.